if we, all right. So let's see if that freezing has gone away. Everything should be nice and normal now. I've switched over internets. I've rebooted my computer 3 times. Hopefully this is going to get us to go. Okay. So welcome to week 11. We're going to do what I consider the beginning of the rest of organic chemistry. We finally got all the ideas of what a nucleophile were, what the mechanisms are, our kinetics versus thermodynamics. And now we're going to actually start what is, nice hardcore chemistry, reactant and product, reactant and product, reactant and product. And so that's what I want to focus on now. So we're going to start module 8 today. And so that means the homework will be due at Friday, November 6th for module 8. And we'll have, of course, lectures Monday, Wednesday, and Friday here at this Zoom code today. All right. And so that's all we'll have going on this week, but we're going to do a lot of cool things with it. So what I'm going to do now is I'm going to switch over and share my screen. And no, you're not seeing that wrong. It's chapter 6. And the reason I wanted to start with this first part of module 6.1 is that we introduced different kinds of organic reactions. And we've actually done 2 of these now, okay? We introduced substitution reactions, and that's where our SN1 and SN2 come from. We have different things that can happen, right? And so that was our first thing. And that's where we learned about nucleophiles and reaction diagrams and all those other things, okay? Now, hand in hand with that, we learned about elimination reactions, our E1 and E2 reactions. And so we've learned, some of the different parameters and what make reactions go forward and reverse. And so that's kind of what we've talked about up to now. Well, our next thing we're going to do is we're going to do the reverse of elimination reaction, which is an addition reaction. We made a double bond, and now we're going to see how we can get different products by going through this, eliminate, and then add something to it. We're going to get a bunch of different functional groups. So you can start with an alkyl halide, do an elimination reaction, add something else to it, and have a new functional group available to you, especially if you had a tertiary compound where it would be very difficult to just get a substitution reaction. So that's where addition reactions come in. But in addition to addition reactions, because of carbocations, we have to be very careful about our rearrangement reactions, okay? Especially when we go from a secondary carbocation to a tertiary carbocation. So that's the other thing that can happen there. And then, of course, the last one, which happened in the last chapter when we were looking at E1 and SN1, we actually had to have this bond cleavage. This bond cleavage happens to give us our carbocation, and it'll pop up again in chapter 10 when we talk about radicals, okay? So bond breaking is that last thing we have. We did see it in our E1 and E1 and SN1 reactions. And so I wanted to say that, we've learned a little bit about that. And then, of course, our last thing is bond formation. Now, this is the second step in a SN1 reaction, right? Because we already have the carbocation and we attack it with a nucleophile. In that reaction at the bottom, we're going to learn a little bit more about that in chapter 10. But I wanted to remind you that we have learned a lot of different ways to do things up to now. And that, the ideas that we'll be moving forward with are coordinate diagrams. So we need to know kind of what steps are happening in our reaction mechanism. Electrophile, nucleophile. Okay, we need to know exactly who the electrophile is and who the nucleophile is, because that'll kind of control the way the reaction is going to run. And the next thing we have to do is we also have to think about acid and base, because what you want it to do is you want to go from the stronger acid to the weaker acid, and that's a driving force in your reaction. Remember, that can be the conjugate acid of one of the derivatives or one of the products. So we need to look at it as a Bronsted-Lowry conjugate acid-base theory to get us to our products that we'll be seeing. And by using nucleophile, electrophile, and the Bronsted-Lowry acid and base, we should be able to pick our major products from all of our next reactions. Okay, so that is the intro I have to our chapter 8 here, our module 8, and it's reactions of alkenes. Okay, so what I like to do in the first part of reactions of alkenes is give you an overview. We're going to learn all these things in this chapter. Okay, so we have several different things that can happen in alkenes, and one of the first things we're going to talk about is we're going to add stuff across it. So everything on this side here is we're adding stuff across that double bond. So that's addition to a double bond, but we have a bunch of different things we can add, and they all give us different functional groups. Okay. So for example, if we add an acid like HBr or HI or HCl, we're going to get a monohalogenated product. Okay. However, if we add something like chlorine or bromine across there, we're going to get a dihalogen product. Okay. So we can select our final product by what we're going to add across that double bond. Now, we can also do the opposite of that dehydration reaction. Remember when we had those alcohols and we added acid and it lost water to give us our alkene? Well, that's a reversible reaction. And we're going to talk about how you can force that back to that alcohol. Now, is that alcohol going to be in the exact same place it was before? Probably not. So we'll have to pay attention to what the stable transition state is. Okay. Now, let's say you wanted a halide plus an alcohol. We have a way to do that. We can start with adding a halogen across there, but in the presence of water, we could have the water act as our nucleophile and give us a halohydrogen reaction, which means a halogen plus an OH. Okay, so that's going to give us some really interesting specificity. Now, notice all these have syn and anti. We'll talk a little bit more about that, but we'll summarize those different addition types at the end of this chapter. But I want to pay attention that we're going to learn a lot of things about how to make a lot of different functional groups in this thing by all using a similar reaction. All of these are addition to alkenes. Now we have a seemingly weird one where we add boron across the system. When we add boron across the system, we have to pay attention to Lewis acid base theory because boron is a Lewis acid and it's going to seemingly add backwards to everything else. And so we have to pay attention to that. And most of the time, we don't just take the boron on there, we actually oxidize it off to give us an alcohol. And because we're oxidizing it off and our boron's acting as a Lewis acid, we actually get it showing up at a different place than if we just added water across the double bond. So we can actually get selectivity of product by doing that. In addition to that, we also have selectivity when we work with mercury. Now, what we do with the oxymercurization, demercurization is we actually put mercury onto our double bond, and then we oxidize it off and giving us an OH in a specific location because the mercury blocks that position and doesn't allow for rearrangement. Okay, so all of those reactions we're going to learn, and all of those are addition across double bonds. Well, then we also have a couple other weird ones we have, and this one is a diol, creating a diol from it, and this is osmium tetroxide. And so this is an oxidation reaction, but it has a different mechanism than the other ones. So we have to pay attention to it and have it separate. Another thing we can actually do is we can react just that double bond and actually break it and turn it into two carbonyl compounds, aldehydes or ketones. And we have a special reaction just for that. And the last thing we can do, it technically is an addition reaction. We can add hydrogen across that double bond. And that can take it all the way back down to a hydrocarbon. So we're basically starting with something with a functional group, doing an elimination reaction to give us an alkene, and then get rid of it so down back to an unfunctionalized hydrocarbon. And we're going to learn all of those in this chapter. Okay, so let's start with the first one, which is hydrohalogenation. Okay, so basically, hydrohalogenation is the reverse of the dehydrohalogenation, which is the E1 or E2 reaction we use to create the alkene. Okay, and the general reaction is we have our alkene. Our alkene has that double bond. That double bond makes it a nucleophile. Okay, so it is looking for somewhere to share those electrons. Okay, so it's searching for an electrophile. Okay, and so we have to think about it in that terms. And when we do, we'll see that the selectivity of the reaction follows those rules of nucleophile, electrophile, and most stable transition state. Okay. So when we start thinking about the alkene as a nucleophile, we're thinking those are the electrons that are going to reach out and grab the electrophile. In the case of an acid like HBr, right? Hydrogen has the plus, bromine has the minus, which means hydrogen is the electrophile. It's the one with the positive charge, okay? So our electrons from our nucleophile, our alkene, are going to reach out and grab that hydrogen, and that's going to give us our transition state. And in this case, it's a carbocation transition state. Okay. So right there, we need to have the most stable carbocation possible. And when you get the most stable carbocation, that's going to drive your reaction mixture. It's going to show you where the bromine is going to act as to make that new sigma bond. So once we've reacted our hydrogen with our alkene, so we had a nucleophile and we reacted it with an electrophile, and now we've created a new species. This new species, this is an electrophile because it has a positive charge. And guess what? We created bromine minus, which is a nucleophile. Okay, so we're going to do another nucleophilic attack. Bromine's going to attack that carbocation to give us our final product, which is our addition across that double bond. Okay, so we can use the entire argument of most stable transition point and nucleophile electrophile in all of these reactions. Okay, and so I'm going to point that out in each and every step of these reactions. Okay, so what this looks like here is we're going to start with two sp2 carbons. These sp2 carbons have that p orbital. Those electrons in that p orbital are going to reach out and grab that hydrogen, creating a new sp3 sigma bond. When we create that new sp3 sigma bond, we now have an empty p orbital, our carbocation, which then can react with any other nucleophile in the area to create another new sigma bond. And the key here is that the electrons from the double bond create our first sigma bond with the hydrogen, and then our electrons from the nucleophile create our second sigma bond with the former alkene, giving us a completely sp3 hybridized carbon system. All right, so does that make sense right now? Okay, and we're going to see the same thing happen again and again and again. So getting this kind of general concept down is really important. Okay, so let's go through the mechanism step by step, because we love doing mechanisms and reaction diagrams, right? Because they tell us what's happening. Okay, so the first step of the reaction is actually trying to create that new transition state, which is having your electrons from your double bond reach out and grab the positive side of your HI or your acid complex, right? It's reaching out and grabbing that hydrogen, okay? When it does that, those electrons from the double bond are used to create our new sigma bond, which gives us our intermediate here, which is our carbocation. Okay, carbocation right here. And then that carbocation has to kind of fight through a little bit of electrostatics to get to the transition state where the electrons from our nucleophile are going to come in and create our new sigma bond. And then that cascades down into products. Most of the time, because alkenes have more potential energy than alkanes, and the bond strengths of these, almost all of these reactions are exothermic overall, okay? So alkenes have more potential energy because of that double bond. Our sp3 hybridized carbons have less potential energy, so it always releases heat. Okay. Now, in this case here, our order of reactivity goes by acid strength. Okay. So the proton in HI is more acidic than the proton in HBr. Therefore, it is more electrophilic. Therefore, it reacts faster. Okay. And so it's HI, HBr, HCl, and HF. It follows exactly along with our pKa's. Okay, so that's why acid strength is important in this particular system. Okay. All right. So now let's do a thing about, because we're forming that intermediate, that carbocation here, that means we want to make sure that our formation of a carbocation forms the most stable carbocation possible. And that happens in our first step, that forming that transition state. Because we're starting to form that carbocation in that transition state, it actually directs which side of that double bond the hydrogen goes to, okay? So what we're seeing here is, let's say we have this compound here. Notice we have two R groups here and two hydrogens here, okay? Which means if we created a carbocation on this carbon here, it's going to give us a tertiary carbocation. And if we created a carbocation here, it's going to give us a primary carbocation. Okay, so just from that argument right here, where do you think that first hydrogen is going to add to? It's going to add to the side that gives us the most stable carbocation. And what that is commonly known as is the hydrogen goes to the side with the most hydrogens. But the underlying reason is that it forms the more stable carbocation. Okay. So let's look at that. Okay, so if this would give us a primary, so if this one would give us a primary carbocation, that means we actually want the carbocation to form on the more stable one, okay? Which means the hydrogen has to go to the least stable side of that double bond. So that means that we have this hydrogen generating this as our intermediate with our tertiary carbocation. It does not go where the hydrogen goes to the other side and give us our primary carbocation. This is what we call Markovnikov's rule. Okay, Markovnikov's rule states that the hydrogen will always go to the side with the more hydrogens. But the reason is that carbocation stability. Okay, which means if the hydrogen always goes to the side with the more hydrogens, that means you have product selectivity here in the fact that your bromine or your nucleophile is going to come in and attach to the more substituted carbon. And so this is going to give you the only product. Okay, so do we understand what the Markovnikov's rule is? And do we understand why the hydrogen always goes to the more side of the hydrogen?
Wasn't our example, didn't our example have two CH3s on both sides though?
No,
Our previous example?
oh, well, that was just a general concept.
Okay.
Okay, so if we had 4 methyl groups on this, then it would give us the same product if it attacked either side, because you just
Okay.
kept the molecule around. But in this case, to explain Markovnikov's rule, we made sure they were completely different.
Okay.
Okay. So, and again, it has everything to do with that transition state, okay? Remember that transition state takes energy. And so if we're forming a transition state and we have to form this partially positive charge on carbon because we're starting to have that hydrogen add to one side, it has a lower activation energy if that partially positive charge is in the tertiary position. If we're trying to add the hydrogen to the other side, such that it gives a primary carbocation, that's a higher energy transition state. Therefore, it has a higher activation energy, which means it's going to go much, much slower. And we're going to get our major product is the one that's going to go through the lower activation energy to give us our more stable intermediate. Okay. Remember, activation energy just means it takes much more energy and therefore goes much, much slower. It doesn't not happen. You might get a little bit of it there, but it is preferred to go with the lowest activation energy, and it always goes faster with the lower activation energy. Okay, so that is hydrohalogenation. It works with all acids, HBr, HI, HCl, etc. Same mechanism every time, and it always follows Markovnikov's rule. Okay, now let's use a different set of electrophile nucleophile. And in this case, we're going to do acid catalyzed hydration. So this is the opposite of that E1, E2 reaction where we take an alcohol, protonate it, and lose water. So we're basically going to do the exact opposite mechanism. So the opposite mechanism would be to protonate water and then have it start to add across a double bond. Okay, so let's see what we do there. So this typically uses a strong acid, usually sulfuric acid. Occasionally you can use other acids. We don't use HBr, HI, or HCl as a catalyst in here. Why? Because it would undergo hydrohalogenation instead of hydration. So we cannot use HBr, HCl, or HI in water to do a hydration reaction. We have to use a different acid. And because nitric acid is an oxidizing acid, we typically use sulfuric acid. So you'll typically see sulfuric acid and water. Okay. So our first step here is going to be, again, the protonation of our water. Why are we protonating the water first? We're protonating the water first to make sure that we have a hydrogen that is more electrophilic, okay? It's sharing those electrons with the oxygen. The oxygen wants to be neutral. And so it's sharing those, it's actually, trying to, this hydrogen is now more electrophilic because the oxygen wants to steal its electrons back to be a neutral compound. And so what we see is that our alkene is our nucleophile. It's going to reach out with its electrons and grab that hydrogen to give us our intermediate. Okay. Notice we don't form the primary carbocation, we form the tertiary carbocation. The primary is not formed, the tertiary is. And it's actually drawn, this is the tertiary carbocation, but it doesn't form the primary. So that should be here. So we're going to get our tertiary carbocation. And what's the great thing about tertiary carbocations? They can wait around for weak nucleophiles. And so the water is a weak nucleophile. It'll wait around until it can use the electrons from that water to make our new sigma bond. When we do that, we now have a protonated alcohol, okay? Which means we have to use another equivalent of water to deprotonate that protonated alcohol, and we regenerate our catalyst of our acidified water, and we gain our neutral alcohol, okay? Notice, each and every one of these steps is reversible, okay? So what does that mean? That means that you can do this reaction to make the alkene by removing water, or you can add water and take an alkene and turn it into an alcohol.
I have a question.
Yes.
Well, it's kind of just a small question, but I was thinking about this for a while. And why does sulfur and sulfuric acid, why does it have 10 electrons in its octet?
Okay, so it's in group
Or
3.
12, I guess, right?
Well, it technically has 10. And you do have, when you go up in size, so sulfur is analogous to oxygen. When you go up in size, it has an extra shell of electrons to play with. And so it technically has the 10 electrons around it. So
Okay.
1, 2, 3, 4, 5, 6. So yeah, 12 electrons around it. Okay. So because sulfur is so big and polarizable, it can. Phosphorus can also have these multiple bonds as well.
Okay.
But anything in group 1, which is, carbon, nitrogen, oxygen, fluorine, cannot. They can only have an octet. Sulfur and phosphorus are 2 of those that kind of break that rule.
Okay.
But technically it's organic chemistry, so we don't talk about it. Inorganic chemistry. All right. Okay, good question though. All right, so when we do acid catalyzed hydrolysis, hydration here, we have to control which product we want to make, okay? If we want the alkene, what we want to do is somehow remove water and use a higher temperature. By having it at a higher temperature, that you're encouraging water to boil out of the reaction. And if you have less water in the reaction, it's going to drive it to the alkene. Now, if you want the alcohol, you want to lower the temperature of the reaction and have a much more water around. Because with much more water around, it can act as the nucleophile and drive the reaction to the alcohol. Okay. So when you want to form the alkene, think higher temperatures because you're driving off water, you're boiling away water. When you want the alcohol, think lower temperatures and adding water to the reaction. Okay, so the full-on mechanism basically follows Markovnikov's rule in the fact that you protonate your water, making it much more, making that hydrogen much more of an electrophile, and it makes it a better target for the alkene to reach out and grab it. But then again, you form your carbocation, and you always form your more stable carbocation. So it's going to give you the hydrogen is going to add to the side with more hydrogens always. And then it'll form that carbocation, and then you lose the acid and you create your final product. Okay. Now, what happens if you don't have water in the reaction? What happens if you have some other nucleophile besides water? Okay. If you have some other nucleophile besides water or a better nucleophile than water, then the first two steps are going to happen the same. You're still going to protonate your alkene, giving us your carbocation, but now your carbocation is going to be attacked by the better nucleophile. Remember, water is a poor nucleophile. If you have a better nucleophile in there, you can. So you can actually do a halogenation reaction with this in the presence without an acid, without an HBr and HCl. You can actually do it with sulfuric acid and some salt of a halide. Okay. It's not the best way to do it, but it can be done. Most people use the acid, the HI and HBr to do the work. Okay. But because we're forming that carbocation, it is possible to do that. Okay, so those are the first two that we have. We're adding water across our double bond. We're adding acid across our double bond, okay? And again, we're looking at the same mechanism of nucleophile, electrophile, intermediate, and products. All right, now let's change up the mechanism a little bit by changing our system, okay? So in the case of adding two halogens across a double bond, we call this halogenation. We're going to put two halogens, one on either side of that double bond. And I'm going to show you why one goes on each side. And it's a slightly different mechanism. Actually, it's a very different mechanism and ends up with a slightly different type of product mixture. Okay. So the general reaction is we take our halogen in this case, and remember that's a non-polar bond, but it's polarizable because those are big fluffy atoms. Okay. And we take a solvent. The solvent has to be one that cannot be halogenated. So you're going to see things like chloroform, carbon tetrachloride, methylene chloride, and acetic acid. Those are going to be the common ones used in this system. And what we're going to do is we're going to take our material, we're going to add one bromine to one side and one bromine to the other side, going from an sp2 carbons to sp3 with that new halogen sigma bond. Okay. Now, when we do that, in this particular case, we have we only have one isomer because of the derivatives. However, when we do it with a cyclohexane, because we're kind of locked in space, we actually get the trans-only isomer. We don't get the cis isomer of the dimero. Okay, so that's a problem, right? If we don't get the cis isomer, that means that there's some kind of restriction in the mechanism that makes it happen only trans. And so we have to think that that's a little different than that other mechanism. The other mechanisms right there go through carbocations, right? So those have a mixture of stereochemistry. Here we have a very specific stereochemistry. It only adds trans, okay? So think about that as we look at the rest of the mechanism of the reaction, okay? So in this part of the here, we have to think of that the idea is that our alkene is our nucleophile, right? So it's the one with the negative charge. Our bromine has a non-polar bond, okay? But because it is such a long bond and they are large atoms and are polarizable. Remember, bromine and iodine were both polarizable nucleophiles. We can actually, as the nucleophile approaches that non-polar bond, it can actually induce a dipole in the system such that one bromine becomes slightly positive, the other bromine becomes slightly negative, okay? So what that's doing is that's polarizing that bond. Once it starts polarizing that bond, that means the electrons from the nucleophile can attach to the bromine, and the electrons that were binding the two bromine together go onto the other bromine, giving us bromide ion, okay? So we have the same thing that's happening as a nucleophile attack, but we have to induce a dipole in the bromine to make it happen. Okay. So what it kind of looks like is we have this electron-rich alkene is acting like a nucleophile and is displacing a halogen ion in a halogen-halogen bond, okay? So we have the alkene reaching out and trying to grab at this bromine that has been polarized. The two electrons creating the sigma bond between the two bromines go off onto the halide as it leaves. Our X now has a negative charge here. And we have our new sigma bond, okay? And our new sigma bond is right next to that empty p orbital. Remember, both electrons from the double bond attached to the halogen, leaving a carbocation out of their system, okay? But because of proximity and the idea that we have electrons available to us in the halogen, they immediately reach over and create a new sigma bond, okay? So our actual major resonance contributor here is the formation of a three-membered ring where we have a bromine attached to two carbons, okay? So this is our intermediate. This is that carbocation is just there for, a very small percent of the time. The major resonance contributor is this three-membered ring. This three-membered ring is what controls reaction selectivity, okay? The formation of this three-membered ring controls where the other nucleophile has to come in and attack it, okay? So the full mechanism is our alkene reaches out, grabs, polarizes the bromine, makes it partially positive, and generates this bromonium ion intermediate here with the three-membered ring. And notice there's a positive charge on bromine here, okay? So we have that positive charge on bromine. Now, if the nucleophile came and attacked this bromine and went backwards, we'd have starting materials. So it could happen, but we would never see it. We would never see it happen. However, if the nucleophile comes on the bottom right here, it has to attack one or the other of these, okay? And when it does, that means it has to attack on the opposite plane from where the bromonium ion intermediate is, and therefore you always get trans addition, okay? Which side does it go on? It's about a 50-50 mixture. It doesn't, once you have it on top here, it can attack this side or this side evenly, and then you end up with only trans products. Remember, on the HI and HBr reaction, you get a mixture because you form a carbocation. In the hydration, you get a mixture because you form a carbocation. Here, the bromine's trapping that carbocation, and we have selectivity of our addition. Okay. I have a question in here. Is the bromine polarized in solvent? Sorta, but it's really being polarized by the alkene. The alkene is what's reaching out with its electrons to induce a polarization in that bond, generating that intermediate. Okay, so do you see why we have selectivity in addition? This is what we call anti-addition. It happens only opposite the other bromine because of this three-membered intermediate trapping a carbocation in that way, so it can only add from the bottom side of the system. This works with straight chains and everything. It's just easier to see in our cyclohexanes. How good a yield is halogenation reactions? You can get, depending on your substrate, if it's not very bulky, 90, 95%, easily obtainable. Now it works mainly with chlorine and bromine. Iodine's a little too reactive, not reactive enough, because the heat is enough to polarize the bond. And fluorine's way too reactive. So we typically, when we do this, only with bromine and chlorine. And notice we don't need a catalyst for this because the alkene is the part polarizing the bond. Okay.
It says sp3 reaction for Br2. So is that just the alkene just like interacts with the specific sp3 reaction to make it positive and negative? That's what's going on.
Well, I mean, the bromine is sp3 hybridized, attaching to the other bromine.
Yeah.
The carbons in the alkene are sp2 hybridized. Now,
Okay.
at the end of the reaction, we now have everybody has an sp3 hybridized alcohol.
Okay. Yeah.
Okay.
Yeah. Because it's, oh yeah, because the sp2 is like negative. So it
Well,
creates,
sp2 has the p orbitals. The p orbitals have electrons that are empty. So we transition from that p orbital not being hybridized to, in our product, all of the orbitals are hybridized.
yeah. Okay.
Okay.
That's nice. Yeah. That makes sense.
So that being said, we know this bridge forms, and it is the major resonance contributor because we do not see any of the syn addition, where the syn addition is where they're adding to the same side right here. And in those in those reactions where we form the carbocation, we get half of it come from the top and half of it come from the bottom. However, in these ones where we trap it in that little triangular, shaped intermediate, we only can have attack at the bottom, so we only get the anti-addition, and in this case, it's the trans product. We do not see syn addition at all. So syn means that both things are adding to the same side of the double bond. Anti means they're adding to the two opposite ends of the double bond. And again, it's easiest to see when you have a cyclohexane because you don't have to worry about free rotation. Okay. And what it also tells us is that we do not actually have a carbocation. Because if we had just a bare carbocation, we would get attack at the top. We would have some syn product, and we would have the same amount of anti-product. But because we don't have any syn product, we only have anti-product, proves that we don't have a carbocation. All right, so, okay. So hydrohalogenation, where we're adding acid across, is syn or anti. You can't tell because you form a carbocation. Hydration is syn and anti. Sometimes you can't tell because you're forming a carbocation. Halogenation is always anti because of that intermediate right here. Now, what if we change up what the attacking nucleophile is after we formed that bromonium ion? Okay. So when we change the nucleophile attacking here, we can have alcohols or water come in and attack, and we call this the Halogenation reaction. In the case of attacking with water, we end up with a halogen and an alcohol in their one, they're one carbon apart, a 1,2 halogen alcohol. And if we attack with an an alcohol, we'll end up with a 1,2 where we have an ether on the other end and a halogen on the other side. So either one will work as a nucleophile in these reactions. So let's look at that a little deeper. So in the presence of a solvent, if you use water as a solvent here, the water itself is not going to react with the double bond without an acid, okay? So just water and bromine does not form acid, and therefore the only thing that can react is the bromine is going to react with the alkene because those electrons are going to reach out and polarize that bromine-bromine bond and give us our bromonium intermediate. Okay. Once we form our bromonium intermediate, we now have bromine as a nucleophile, but we also have water as a nucleophile. Okay, but bromine's a much better nucleophile. But if you're using water as a solvent, there's so much more of it around. The probability of it attacking is very high. And when it does, we actually end up generating our protonated alcohol species, which then water acts as a base, and it goes to products. Okay, now notice one of the products you do form is HBr at this point. But if you have a lot of water in there, you're diluting it out. So one of the products you might end up as a minor byproduct is going to be the addition of 2 bromines on there. And we see that here because you did form a little HBr. Okay, where's my, oh, there it is. So you can form a little bit of this because another bromine can come in and attack. But because you have so much more water, your major product is going to be the anti-addition, and it's an antimer, the anti-addition of the halohydride or the alkyl halide alcohol. So, okay, So, and the only thing we changed here was the solvent. We went from a chlorinated solvent or a halogenated solvent like carbon tetrachloride or chloroform to water, and water being that weak nucleophile participates in the reaction. Okay, but again, because we form that intermediate, we always have anti-addition. All right, questions on that? Okay, so what I think you might want to do to help kind of get this together in your head is we're going to end up with a table that says the type of reaction, whether it's syn and anti, and any kind of other things that might help or hurt the reaction. For example, the hydration reaction is reversible. So by adding water or heat, adding heat, you're going to get your alkene. Adding water and lowering the heat, you're going to get your alcohol. So we're going to come up with a table, and it'll be toward the end here. Okay. So in the case of when we don't have that ring and we're not looking at two identical carbons, so the best way to studying is practice the drawing molecules and memorizing a table. I think the best way to do it is to find a way to do a compare and contrast between, okay, this reaction only uses this and these are the products. This reaction only uses this and gets these products. So kind of a compare and contrast. And then practice where, okay, these are my reagents. What are my product going to be? This is my substrate. What am my product going to be? Kind of almost do a random card deck of reactants and substrates, and then see what your major products are and double test your knowledge. Okay? Okay, so now let's think about this in the terms of Markovnikovs and anti-Markovnikovs. How are we going to do this? Okay, so in the electrophilic addition of these alkenes, we do add in a Markovnikovs-like fashion. But you have to think about what Markovnikovs mean. Markovnikov means that the thing that's being pulled in as the electrophile is going to go to the less substituted product, okay? Meaning you're going to form your most positive charge on your more substituted carbon, okay? So the first step in adding our halogen across this double bond is to create our three-membered ring, okay? But those two carbons now have different priorities. One would give us a primary carbocation, one would give us a tertiary carbocation. So that being said, the one that's going to give us a tertiary carbocation is actually going to be more electropositive, and it is the site where the incoming nucleophile will attack. Okay, because they're not equal. When we had that alkene, when we had the cyclohexane here, they were equal because they would both give secondary carbocation. So it doesn't matter which side it was on. Okay. In this case here, we're going to be able to form a tertiary carbocation or a primary carbocation. So that means the incoming nucleophile is going to see that that tertiary site is more electropositive, more like a carbocation. It's not a full carbocation because we have this bond between the bromine in it, but it's the more positive side of the bond. If it's the more positive side of the bond, that's where the nucleophile is going to come in and react, giving us our primary product right here is a Markovnikovs addition. But you remember, our bromine added first, and our other ones, the hydrogen added first. Our bromine in this case is analogous to our hydrogen, and therefore it does follow Markovnikovs rule. Okay, so questions on that? I want to actually do boron as a separate lecture next time, but I do want to go down to my summary table here because I want you to get an idea of where we're going to go with this summary table that we should start building now.
The Markovnikovs rule says that it'll bind to the area, so it produces the more stable carbocation.
Correct.
Okay.
So another way to think about it is that the thing that comes in first is going to be on the least
carbonated side.
Substituted side, right?
Or substituted side, yeah.
Right. Okay. So this is the summary with stereochemistry on it that I wanted you to start building yourself, okay? In reactions that yield a mixture of syn and anti, those are the ones that have something come in and form a carbocation. And we've already learned that the hydrohalogenation does and the acid catalyzed hydration does. Okay, we're going to talk about these next time, so don't worry about those yet. We learned that we have one reaction that's syn on, oh, we haven't learned that one yet, never mind. But then we have learned that there is a reaction that does anti only. These anti-onlys are the halogenation and the hydrohalogenation. So we've learned that we have anti-specific reactions, and that's important. We've learned that we have mixture reactions, syn and anti there. And next time we're going to learn our syn-only addition. Okay. So this is what I was talking about by trying to get a summary slide to where you get the concepts all in one page and do a compare and contrast. Okay. So, and we'll actually fill in the rest of this table after we talk about boronation and mercurization in our next lecture. Okay. And then our last lecture is going to be on alkynes and all the different cool reactions they do for this week. Okay. Questions for this part of the chapter so far? Okay, well, in next lecture, we're going to pick up with boronation. Let me see, let's go back to the right slide so I don't forget. Yeah, we're going to start with hydroboration oxidation of alkenes and how it does seemingly anti-Markovnikov addition, but you'll see why it actually follows. Nick has a quick thing about SI sessions before you go away. Don't leave yet.
Hi, everybody. So believe it or not, we have about 5 more weeks left in the semester. And this is the last week to complete your credit for attending sessions. So you can attend up to 2 sessions for credit this week. And then after this week, sessions are no longer for a grade. But I'll be here for the rest of the semester. Don't worry. I just wanted to let y'all know that you have the rest of this week to get credit for, I think it's your 10 sessions of the semester.
Are there no
If you
more
haven't-
SI sessions?
There will be. They're just no longer for a grade in the class. But I'll be here every week, same sessions. Nothing's changing. You just are no longer graded for it.
Okay.
If you ever have any questions,
If we attended every week, how many would we have attended?
if you attended every week, you have your 10 sessions by now. In fact, I think you might have 11.
Okay, then I'm
If you attend this
good.
week-
I missed one week, so I was like wondering.
If you want to check how many sessions you have attended, you can go to Texas State Slack, and then it lets you check your attendance. The instructions are also on Dr. Irvin's syllabus. But if you have any questions, feel free to reach out to me at any time. Yeah, come to sessions today at 2 if you want to review today's lecture.
And I can
Cool.
encourage you to continue going to SI sessions because this, this nailing down the compare and contrast and the subtle differences between the reactions, that's what's going to be discussed in these SI sessions. So I highly encourage you to, just get this really clear in your head and get that opportunity to do that peer-to-peer kind of, non-confrontational information transfer.
It'll be
Okay.
fun. All right. Thanks, everybody.
All right. Thank you, everybody. And I'm going to go ahead and end now.